Hi everyone, I'm Sean. I'm a third year EECS major here at Berkeley. And a little bit about me, I'm one of the UGSIs for EECS 126, which is a probability class here at Berkeley. And I really enjoy video games and rock climbing. So this week, I'll be talking about a bit about the bias-variance trade-off and regularization. This is one of my favorite topics that we teach here because it combines high-level mathematical intuition with really useful and practical skills that data scientists and machine learning people have to use on a pretty frequent basis. And a little bit about the headphones, I have to wear these right now because the microphone on my computer is very busted. So let's get on with the lesson. So generally, I can categorize models into three distinct categories: models that underfit data, models that overfit data, and models that are correct. So what I mean by underfitting is if we look at the model on the left, the model is a line, whereas the data is like an arch, or it's like a parabola. So the model isn't really complex enough to describe the underlying data. And no matter which line I pick, I can never get something that can accurately fit the data. So this is what we refer to as underfitting, and it results in high bias. So the case on the right is kind of the opposite issue. The model is way more complex than it needs to be. So it actually starts to fit the noise in the data rather than the true underlying signal, which is a parabola. So you get this like very, very like specific model for the specific data set, but you actually want something general that can generalize to all possible data that you could see. That's not only in this data set, but that's out there in the world. And the model in the middle is just right. It's complex enough to describe the data, but not any more complex than that. And that is what we're aiming for. Cool. So let's continue with the thought experiment. So in your head, try to build a model of a dog. Just take a minute and think about it. And we're going to use this model to classify dogs. So if we look at the model on the right, it's way too specific to be a classifier because not all dogs are lying down happily in a field of grass and are white and short and fluffy. Like there are a lot of different types of dogs, and this is just too specific to be a good model to represent all dogs. However, if we look at the picture on the left, this is not what a dog really looks like. It's not really, it doesn't have the correct structure to model a dog in real life. However, if we look in the middle, we can see something that is just complex enough so that it can describe a dog, and then a dog could be classified by this, but it's not too specific to exclude real dogs from our model. Although I can think of some dogs that don't look like this, so I'm not sure if this is like the best example. And bias-variance trade-off is one of the most useful skills, or one of the most useful topics to know as a data scientist, because a lot of the work that we do is in fine-tuning models and picking a good model for our data. So being able to recognize when we overfit or underfit data is like very, very important. Some people might instinctively feel that bias is worse than variance because bias has like negative connotations in a society. And this isn't completely fair because variance can also be very bad. So you shouldn't really think of one being better or worse than the other, but trying to get a good balance of minimizing both at the same time. We can never really get rid of either completely, and we need to find a good middle ground between reducing both. So let's continue to the mean squared error, which is important to understanding concepts that are further down in this lecture. So the mean squared error is the average in the distance between a true data point, which is y, and our prediction from the model, which is f of x. And then we square these values. So let's continue with bias. Bias, the formal definition, is a measure of how close our prediction is to the actual value on an average from an average model. So this is kind of a tongue twister and it's a bit confusing. So I'll explain it with a real life analogy. So let's say that I'm constructing a model of the price of a home. And to construct this model, I'm going to go to 100 different randomly chosen homes. I'm going to take measurements of these homes, like the number of bathrooms, the location, the square footage, stuff like that. And I'm going to use this data to construct a model. And then I'm going to take the measurements of my home and plug these into the model and see the predicted value of my home. So if the true value of my home is $100,000, and no matter what data I feed my model is consistently predicting the value of my home to be $50,000, then I can say that my model is biased because the average result of the model's prediction is consistently lower than the true value. One important thing to note here is that bias really only exists in the context of a set of models and their average. So in other words, just because after a single data set, after you give a model a single data set and train on it, it has a difference between that predicted value and the true value, I can't really say that my model is biased. Bias only exists on a multitude of models trained on a lot of different data. And that if the average of those models is still different from the true value, then I can say that bias exists. Now let's talk about variance. So variance is variance in the traditional sense that you might have learned in a statistics class, except now that it relates to the distribution of models. And this is a bit hard to think about because, with a normal random variable, it's kind of easy to define what variance is, right? But variance of models is much harder to define. And it's actually really hard to compute in real life. So people never really calculate variance precisely and more talk about it as a concept. But when we talk about variance here, we're talking about the variance in the distribution of models. So returning to our old analogy, let's say that after training on 100 different homes, the model, I plug in the features of my house, and then the model tells me that my house is worth $70,000. I think this is a bit odd, so now I go to 100 different homes. Using the same methodology, I train a different model from that different data set. And now that data tells me that my home is worth $130,000. So even if I take the average of all of these model outputs, and that average approaches to $100,000 as n approaches infinity, this model still feels off in that, like, the accuracy just isn't there. I think that the infographic that we have here is a really good illustration between the contrast between bias and variance. So having high variance, as we can see here, means that even though I have the average of my results be correct, so if I take all of these points and compute their average, even though that is correct in the center of the bullseye, each individual prediction is still pretty off from the center. So the model isn't super useful. But having a biased model means that even though my predictions cluster around some value very tightly, this value is off from the true center, and that is referred to as high bias. So let's talk about the trade-off more concretely. So when we talk about mean squared error, as I was describing earlier, we can actually break that up into 3 different terms: noise variance, bias squared, and variance. Noise variance is irreducible noise. It is noise that I cannot avoid no matter what. So it's impossible for me to get a model with 0 mean squared error because there is at least some noise variance. Bias squared is the square of the bias I was referring to earlier, and similarly variance is the variance I was talking about earlier. But one thing that we can see here is that the bias and variance are inverse to each other, in that when bias is low, variance tends to be high. And moreover, we can reduce bias by increasing the complexity of our models, but variance tends to increase as we increase model complexity. When we talk about reducing mean squared error, we're talking about reducing the combination of bias and variance. So if I do nothing to reduce the variance of my models, as in least squares, I am essentially letting my model have very low bias here, but I'm letting it have high variance. What I want to do is find a model that has lower complexity, but has a correspondingly more optimal model complexity. And I'll talk about this a bit more concretely. So if this doesn't make sense, don't worry. Let's continue with polynomial regression. So as a brief recap, polynomial regression is essentially saying, of all of the polynomials of up to degree d, which one will have the best fit of the data such that I minimize mean squared error? And polynomial regression really illustrates the bias-variance trade-off. And before we start, think about what will happen to the bias-variance trade-off as I increase my degree d. And let's see. So I have my true distribution in red, and then I'm going to illustrate a bunch of different models that try to fit this data. So here I have degree 0, which is just a straight line. And then I gradually increase the complexity of my model by increasing the degree of the polynomial that I'm fitting. And eventually, we start off with stuff that obviously is not complex enough to describe our model. However, eventually, as we increase the degree, we see stuff that begins to feel a bit unreasonable. As in, this model in blue here models the bias variance trade-off because as degree d increases, we see that the model is beginning to fit the noise. So returning to our question in the beginning, we can see that as the degree of our polynomial increases and as complexity increases, we have lower bias but higher variance. And that's our first attendance question, which is what happens in polynomial regression as you increase the degree? And that's we get lower bias but higher variance. Okay, I tripped myself up a bit. Cool. And we can see that as the degree increases to 10 and 13, our predictions just fit way too much of the noise in the model, and the true distribution is almost completely lost. And that's something that we really want to avoid. So now we think to ourselves, how can we combat overfitting? We use gradient descent as a way to reduce bias. So if we look at our original mean squared error definition that we reduce in standard linear regression, we are reducing the distance between the true data set value y and our predicted value f of x squared. And this is very similar to the bias squared term. So kind of baked in to standard linear regression, we are inherently always trying to reduce the bias. However, we have no real way of reducing the variance of our models. And that is what regularization is really about. And as a brief side note, I might refer to the linear regression we've been talking about, like standard linear regression, as ordinary linear regression, or OLS. And these are very standard terms. So regularization is basically is a method of trying to reduce the variance of a model alongside the bias. So standard models already try to reduce bias, but now we're going to try to tackle variance on top of that. And the standard way to approach this is to attach a regularization penalty to our loss in the model. And this takes a form of lambda times r of theta. Lambda is a hyperparameter that we will give to the program ahead of time and that we won't train. And this lambda is determined by fine-tuning our model manually most of the time. Theta is our weight vector, and r of theta is an estimate as to the complexity of this weight vector. And essentially what we're doing is we're trying to guess how complex a model is by the weights it has by the weights of the model. So this is kind of like an abstract way of thinking. There's no conclusive way to prove that, my proxy for how complex I think a model is truly correct. However, there's two really popular ways of trying to describe the complexity of a model through its weights. And as a recap, the weights of a model are described by the vector theta. The first is through ridge regression, in which we take the sum of the squares of the weight vectors. So if my weight vector was the list A comma B, then the ridge penalty would be A squared plus B squared. Lasso, on the other hand, uses the absolute value of weights instead of their squares. So if my weight vector was A comma B, the lasso penalty would be the absolute value of A plus the absolute value of B. And there are specific instances in which you would want to use one over the other. And we'll talk a bit about that later. So intuitively, the more we increase our regularization penalty lambda, the more we will reduce variance. But let's think about what happens if we set the lambda value to be equal to 0. In this case, we essentially zero out the term lambda times r of theta, which means that we have our original expression as in ordinary least squares, which is just y minus f of x squared. All right, let's start with ridge regression. So ridge regression is as we described earlier, a specific implementation of regularization in which we fix R theta to be the L2 norm of theta. And a really, really useful property of ridge regression is the fact that it has a closed form solution. So I don't need to use gradient descent to find the solution to ridge regression, although it is certainly possible. And this closed form solution takes the form of adding a term of lambda times I to the inverted matrix in ordinary least squares. So this is the solution to ordinary least squares over here, and we're just adding the lambda times I term into here. And this also gives us a really, really nice property in that for most values of lambda, this matrix, x transpose x plus lambda I, will be invertible, which means that we will have a valid solution to our ridge regression. Whereas this is not necessarily true for standard ordinary least squares. One thing to think about is what restrictions can we put on lambda? Can lambda be negative? So the answer is mostly no. You always want to set lambda as a positive value because you want to attribute penalty to high variance. You don't want to reward it. However, there are specific applications in which you would want a negative lambda value, namely total least squares. This is outside the scope of this lecture, but if you're interested, just Google total least squares, and there's like some fascinating stuff in there. Cool. This is time for our second attendance question, which is, what are the two most popular forms of regularization functions? As we described earlier, the answers to these are the ridge regression and lasso, which are the L2 norm and L1 norm, respectively. In the answers, you can just write ridge and lasso. All right. So let's apply our knowledge on ridge regression to a real world scenario. And more specifically, we're going to use the example we used last week. So first, we're going to read in our data, and we're going to do a bit of data cleaning. And then we're going to do a really important step, which is to split our data between a training set and a test set. So think to yourself about, why do we need to split between a training set and a test set? It's because we want to test the generalization of a model. So we don't really care about how well a model performs in the data we train. We really want to see how well a model performs against data it has never seen before. And this is the essential part of regularization. It helps models generalize to data it has never seen before by avoiding overfitting. And this step here, where we split between testing and training sets, is really important. And the more observant of you may have seen that we are splitting between validation and test sets. And these are similar, but they have a crucial distinction, which we will talk about later in the lecture. So let's set up this least squares problem. So first, we construct our polynomial feature matrix by using the numpy.bander function. And then we set up test and validation data accordingly. We create the linear regression model. We fit the data. And then we look at the predictions of our linear model. we then look at the loss from that model as well as its corresponding R-squared value. Feel free to pause and understand the code. I'm like basically breezing through the code. We see that we have a root mean squared error as well as an R2 value. So let's do the same thing for ridge regression. We can see that the root mean squared of ridge regression is actually better than linear regression, which is what we expect. Ridge regression helps generalize our model to the training set. However, if we had tested our model on the training data, we would expect that linear regression would actually perform better than ridge regression because it kind of fits the noise and the minutia of the training data that ridge regression doesn't do. However, this isn't behavior we really want to see. So the key takeaway here is that ridge regression, if you select your value of lambda carefully, often outperforms linear regression in terms of validation and test accuracy. So the final note on ridge regression is the topic of robustness. And if you don't completely understand this, it's okay. I don't really talk about it more for the rest of this lecture, but I think it's super cool. So it turns out with linear regression and ordinary least squares, I can describe the weight space as a linear combination with weights 1 over S, where S is a singular value of the matrix X transpose X. And the important thing to note is that when that matrix X transpose X is almost not invertible, then these values of S are very small, or some particular values of S are very small. And the matrix I'm referring to is this matrix over here, right? X transpose X. However, if the value of S is really small, then its corresponding weight in ordinary least squares becomes very large, and it tends to dominate the expression. However, the closed form of ridge has a slightly different weight of S over S squared plus lambda. And this essentially suppresses really, really small values of S. And essentially what this does is you lose out on some data because you kind of want to express small singular values, and ridge regression doesn't really do that, but it helps protect the model from these like very, very, very large terms that can arise if the X transpose X matrix is almost not invertible. And you might think about like, what's like the real negative downside of having this scenario? It's that if you have like really small singular values in least squares, your overall model becomes like very, very sensitive to small changes in your data, if those changes correspond with those small singular values. So even changing like an entry of your data by like maybe 1% might throw off your model by like 15%. And that's something that you don't really want to do if you want consistency. Let's move on to lasso. Lasso is an alternative approach to setting the regularization penalty such that instead of using the sum of the squares of the weights, we're using the sum of the absolute values. And the important part of lasso, and the reason why people use it at all, is that it induces sparsity. And this is our next attendance question. What does it mean to induce sparsity? Well, sparsity inducing means that I reduce the number of non-zero weights. So let's think about when this might be useful. Let's say that I have some data set of like 1 million, or I have some model of like 1 million weights, but this is like really, really expensive to like train, like compute and deploy. So I want something like smaller and more memory efficient. So I might use Lasso to reduce the number of weights I have to maybe 100,000. And Lasso will naturally select the most important weights to keep and setting the rest to 0. And this is like super, super useful if you want like something to fit in a smaller amount of memory on your computer. So here we see the same Python setup that we've used for ordinary least squares in ridge regression. And we see that the root mean squared of the Lasso model is competitive with the root mean squared error of the ridge model. Let's consider the intuition behind Lasso and why it induces sparsity. So to illustrate this, let's plot out the function's absolute value of w and w squared. We notice that when w is small, in that it is between -1 and 1, the Lasso penalty of the absolute value of w is actually considerably larger than w squared. So from a high level like idea, ridge will reduce the weight from like very high values up to the domain 1 and -1, but after that, it'll really struggle to push down the value of a weight to 0. And to further build off of that, consider the derivatives of these functions. The derivative of w squared is 2w, and the derivative of the absolute value of w is the sine of w. So it's either 1 or -1. So if w is like really small, it's like 1 over a million, the derivative of w squared is going to be 2 over 1 million, which is basically 0. So if we consider our model from the perspective of gradient descent always moves along the derivative, right? So if you're at a point where w equals to like 2 over a million, gradient descent sees that derivative, and that derivative is essentially 0. So gradient descent will not move along that direction. So in a sense, if we use only ridge regression, we can never really get a model to force the value of a weight down to 0. However, if we use Lasso, the derivative of our regularization penalty is always going to be like either 1 or like -1. So the gradient descent algorithm always has like some gradient to go along that it doesn't have in ridge regression. So here we can see actually like the results of an empirical study done on this. And you can see that the x-axis is the lambda values that you have, and the y values are the weights. So intuitively, if you increase the values of lambda, you are like incentivizing your model to have smaller and smaller weights. So you can see that the weights of this model under ridge regression get smaller and smaller like really quickly as you increase lambda. But then they kind of just like trickle off. It's really hard to push them down that like extra bit, right? So like here they have like really, really small values, but they're not quite 0. So we haven't induced sparsity yet. However, if we look at Lasso, as we increase our lambda, we can see that the weights very, very quickly go down to 0. And if we want sparsity, that's what we want. We want weights of 0. We don't want small weights, we want weights of 0. And here we'll set up our own experiment to kind of see this. So a really important part of the bias variance trade-off is finding a value of lambda that is high enough so that we don't get excessive variance, but is not so high that it makes our model have excessive bias. Because when we have really high values of lambda, that's essentially telling our model to reduce its complexity so that our model might fitting the minutia of the underlying model of the data. What I mean by this is, let's look at a bunch of different plots with different values of lambda, and we run ridge regression on this data. So here we see that with a lambda value of 0, we have like too much variance. Like the model that we have will go up and then down and then up and then down, then up. Whereas the true data distribution is much more smooth. Once we get like higher values of lambda, we get something that begins to like replicate the smoothness of this curve, right? And then it becomes smoother and smoother, which is what we want. But then eventually we get like a flat line once we make lambda too big. Like if we look at this part of the data right here, we get something that is like too flat. And eventually we get something that is just like completely flat and actually goes like the other way. It goes up instead of down. So in a sense, we've wanted like something that like gently goes up and then down as our predicted model. But if we set lambda to be too low, then we get something very bumpy as our model tries to fit the noise of our data. But if we set something like too high as lambda, we just lose the complexity needed to really model this data. And we want something in the middle, like perhaps a lambda value of like 1 that is like in the Goldilocks zone. I wanted to talk a little bit more about one last thing on lasso, which is if we considered going from ridge to lasso to induce sparsity, we've reduced the exponent of the regularization term from 2 to 1. We went from like w squared to w. So what would happen if we went from w to the power of 0.5? Like we further reduced the exponent. Would this induce more sparsity? And the answer is no. And this is our fourth attendance question. And the reason why is that if I reduce the exponent below 1, then my model becomes non-convex. And this leads me to have a lot of problems with training my model across local minima. So if you remember in gradient descent, when there was like a valley, so to say, it was really easy for the model to get stuck in that valley. And even if that local minimum was not the global minimum, gradient descent would converge to that. So the term like x to the square root of x is not a convex function. So we can't really use that as our regularization term. But I think it's a pretty cool idea. So next we're going to go on validation with lambda, and this is a part that you guys will do. So we have a bunch of different lambda values from 0 to 200, and we want you to create models with ridge and lasso, train these models, and report the test error that you get with these models. And one really important thing is to train the data and test the data on different data sets. Because if you test the data set, if you test on the data set that you trained on, you will always get that a lambda value of 0 is optimal. And that isn't correct, because you want to test generalization as well as overall accuracy, not just like the best training error you could get. So then we're going to move on to like really the nitty gritty of validation. So validation has three parts. Or I should say general machine learning has three parts. So the first part is to actually construct and train our model. And we use this with training data, which is the majority of our data, typically around 80%. The next is validation data, which is around 15%. And these are to fine tune our hyperparameters and maybe like change model architectures. So we are improving our model on like a high level and trying to like iteratively improve its performance. The final and most important piece of data, typically around 5%, is to test the model. And the test data can only be used once. You cannot like validate or train your model on test data. That's considered cheating, and cheating is bad. So let's say that you have like a rather limited amount of data. A potential reason might be like you are using like medical data and there just isn't that much that you can find, or you're trying to train robots and like the amount of data is limited by like the movement of the robot. So you can use a method called k-folds validation, in which you split your data into k different segments, and then each segment will serve as the validation segment once. So you can see in this diagram here, in the first run of the program, the first segment serves as the validation data, and the next 4 segments serve as the training data. And then the second iteration sees the second segment serve as the validation, and so on. And what we noticed here, or what we notice here, is that each data is being used, each piece of data is being used in like multiple fashions. So we can like essentially use data more than once. And then to get the overall performance, we'll just average the performance across these k-folds, so to say. So essentially, k-folds validation is a way to use data more efficiently. And then finally, we see that as you train a program more and more, you will always get lower training error, but it's possible that you might get higher test error because you start to overfit the data if you train for too long. So this is a pattern that you should be familiar with and try to avoid. And then these diagrams highlight this pretty well. And then finally, I'm going to go through some scenarios with like different amounts of training error and test error, or validation error, I should say. So if I have high training error and high validation error, what would my model be like? Well, then my model would likely have high bias. The overall like structure of my model is not correct. It's either like the wrong idea or it's not complex enough to fit my data. Next, if I have low training error but high validation error, then I have an issue with overfitting, in that I don't have a model that can generalize to new data very well. Like I've been training on the training data, but then once I move to a different data set to test on, my performance degrades. And this is evidence of overfitting. And then the final piece of, or the final case is that we have low training error and low validation error, in which our model most likely performs pretty well. And then now we have our final attendance question, which are, what are the 3 pieces of data that we work with? And then the answer to this, as we've discussed earlier are training data, validation data, and test data. Okay, cool. So, sorry. As a brief recap of our lesson, we've introduced two general problems with machine learning, which are bias and variance. And you have to control each of them. And oftentimes the best models have a combination of low bias and low variance. Regularization is a way to tackle high variance. And the two forms of regularization we looked at are ridge regression and lasso regression. And we also learned about splitting the data into training sets, validation sets, and test sets. And I think that should be all. If you have questions, feel free to reach any of us on the education team. And I hope you're staying safe. I think that's it. Yeah.